Okay, and I think we should be live again. So, welcome. I did one thing offline because I wasn't sure how long that will take. I integrated Google Test into our project. Uh, the end it was actually pretty straightforward. So there's basically this file that you just copy from the Google Test documentation, and then there's like a bit of code to set it up and integrate, and then adding tests is basically you would add an executable, you link it against the test main, and then just register it as a test. And I'm using CLAN, so it actually pops up here as a test, and I can just, compile it and run it. So yeah, that's working good. So we can actually write tests, which is good because one thing I kind of realized is the Sudoku square is kind of a class that will not really change as far as the interface goes. Like this should be very much the final interface, and we probably won't even touch the implementation too much um, because all of this is pretty minimal and straightforward. So we can just call this, good enough and prepare some tests for this. One thing I realized was that I definitely don't want to have the non-parametric constructor for this class because then I don't have the max value and nothing makes sense. Right. So actually, let's just start with that. Let's just prepare some tests to make sure that things are working correctly. Um, so let me just copy this thing here. Okay. Um, so I already have a very minimal test here. Just basically to test if the testing framework is working. And we can kind of start from there. So if we have an empty square that basically just was initialized, first of all, like it doesn't have a value. The count possible returns the same as the size. So all the values are possible. Uh, let's just uh, make this an actual hard test to ensure that indeed all the values are possible. So we will just do is possible, and we actually expect this to be true. Um, okay, so is possible we have, count possible we have, is set, what was is set doing again? Oh yeah, is set returns better, we have specific value which we don't have, so expect false. Then value I'm already testing, it returns 0. Next. So if I call it this, actually, Um, yeah, like this. So if I call it with a value of anything that's inside, which is 1 to 9, but minus 1, I kind of expect the next to just return the plus 1. So that's very easy to test. We will do next I, and we expect I plus 1. I don't really have to annotate this. Then reset. I mean, reset will not do anything for this, but we can definitely try to do a set and remove. So let's first do a set. So we will just do set it to a 3, for example. And now everything changes. So we expect value to return 3, of course, because we just set it to value 3. Then we expect is possible. Oh, obviously this is kind of not really a test, but sure. Then count possible should be 1. Should be, oops. Is set should be true. Next. So next on a 0 should return a 3. And I think next on 3 should return a 0. Right, what else? Well, now we can do the reset. And at this point, we should be back to basically these conditions again. Okay. So let's see if things actually work. Yep, seems like everything is okay. We can play with this more later, but this was just like a, let's just have a very basic sanity check test. If I, break something completely, that's good to have. So we do have this thing, and last time I was kind of wondering what's happening with our performance, and actually I did try to run perf. And as you will see, the results are not very surprising actually, which means that doesn't really tell us a lot. Plus I'm running this in a virtual box, which is not great to do with perf because like perf is a CPU based counter thingy. So yeah, okay. So if you look at it, like 85% of time was spent in block check or check, which kind of makes sense since we code this for like everywhere and all the time. So yeah, not a very useful profile, honestly. But we can definitely have a look at check and try to make it a bit better. But last time when we ended, we had a problem because if I go back to my main, so there's this commented piece of code. Well, turns out that this piece of code is actually breaking our server, and I wanted to have a look at what the heck is happening. One thing that we really need to do is kind of introduce a debug print of our Sudoku, because right now, let me just comment this again. And if I go back to my Sudoku, so right now it will try to calculate for a bit, and it just prints out the filled in grid. But if you actually want to look at what the heck is happening, don't like right now, each of these cells is basically a bit set of 1 to 9. And we kind of want to see what's inside of that bit set. So I really need some sort of debug print on top of my Sudoku. And I think I need to introduce it into the Sudoku square. And I think I will just do it this way. So how do I want to represent it? So I could do something like this, right? And have, I don't know, something like this. I could use like straight up ones and zeros, but that's, or maybe like this. I think I'm kind of fond of doing this kind of thing. Or maybe even better, like if I just do something like this. So basically just print out the numbers that are still possible. Because this way, if I just look at it, I don't have to like try to match up what like which bit is which and not. Yeah, okay. I am kind of fond of this kind of output. So let's do that. Um, max. And okay, so if the number is possible, I want to print out the number. Oh, but I also want to make it work with 16 by 16. So this will be slightly more complicated. Okay, so for 10, I just want to print out an A and then going forward from there. Otherwise, I just print out the number. Um, no, actually, so this should be 9 because the indexing is a little bit off. Okay. And if it's not possible, we just print out a dot. Okay. And now we need to introduce the same thing on our Sudoku class. And here I just want to go over all the data. Actually, now I'm inside of the class, so I can go straight to data. Right. And what I want to do is debug print it, and then add the space, and here a new line. Okay. So after each element, we just add a space and then a new line after each row. That should work. So now we can have a look at the result of our pruning. Yep. Okay. Hey, Dewcraft, no, I'm not a pro game. And just run it. Okay. So now we have a very nice output, and we can actually stare at this and try to figure out if things are working correctly. So let's just verify if the pruning works as intended. So we have removed a 2 from this block, which makes sense because there's 2 here. We have removed a 3, which comes from this row, from this specific space. 2, 3, 4 we removed because of this thing. 6 we removed because of this thing. 8 we removed because of this thing. Okay, so just like having a very rough look at this looks correct, which kind of tells me that the problem actually might be... Okay, probably, since this looks correct, the problem maybe is in the solver then. So okay, this is very interesting. Yeah, I mean, I'm just staring at the output, and the output does really look correct. So then what can be wrong? One option is the find empty is broken and it doesn't return the correct thing. So what do we do in find empty? We just go through, check if it is set. Is set is just count simple one. So yeah, that should be fine. Uh, yep. Okay, that seems to be okay. Puzzle is filled if all things are set. That's also correct. Check puzzle. Check. Yeah, so all blocks return, everything is okay. Yeah, that all seems fine. So okay, so what do we do here? We store the original value, then get the next. Oh, I know what's happening, maybe. No, that should be fine. I was thinking that when we recursively call this, huh, this is very curious. Okay, let's just not to try to stare at the code just without anything. Let's just actually try to look at some things happening. Right. So, and found this recommendation that I should use the nice calculator, which can actually show me the bits, which is perfect. Okay. So we are looking at, wait a second, next. Unfortunately, next got optimized out. That's annoying. Let me go and quickly change this. Didn't really want to rerun. I wanted to do debug. Okay. So now I actually have stuff. Okay. So yeah, so this is actually, we are staring at the yes, okay, we are staring at this space. So the first time we enter, the next one is 1, so that makes perfect sense. Okay. So then for the next one, we go to here, which is again 1. Yeah, but that should bump out because check is wrong, which means we are here again. And now we are calling it with Yes, now we're guessing it's a 2. And does that... Yeah, so 2 is still a possibility. That works. Okay, so now we move to the next one, right? We're guessing a 5. Yup, that makes sense because we already eliminated 1. So now we are looking at the 4th space. So 0, 1, 2, 3, 4. We will again guess 1 and a 2, but that will be nonsense. And one more time, yes. Yep, yep, yep. Now we're guessing a 5. Uh-huh, that makes sense. Now we're guessing a 6. Yep. Guessing a 2, 5. Guessing a 6. Yeah, and we should end up with 7. Yep, 7 goes through. And we are here. We are starting with a 5. We should end up on 9. 9, yes. Uh, and we jump to here, yes. Okay. Huh. This is very curious because this actually seems to be working fine. Um, which kind of makes me think that there's something wrong with our backtracking path. Which, I mean, there shouldn't really be anything fancy here. Like, I mean, I just store the original. I try all the options I could try. Um, and if I like none of them work, I just restore the original and go back. Hmm. What could be the problem here? Okay, in the second row, I just keep going. Ah, okay, we have the first time we are coming back. So 0, 1, 2, 3, 4. Now we are guessing this. Okay, so the original was, yeah, the original was 492. Uh, which means 1, 2, 3, 4, 3 and 4, 5 and 6, 7, 8. No, 6, 7, 8, yes. Hmm. Okay, so this just seemed to work. Like this restores. Oops, what did I do? This restores the, yeah, the data just fine. Um, this is so interesting that it works without the pruning, and the pruning seems to work correctly, but it breaks with the pruning. I mean, this really makes me think that there's something weird going on somewhere, something very silly. It's like the check doesn't correctly check or something like that. Hmm. Okay, we will need to go the hard way and actually do our due diligence because we simply cannot see a problem just like staring at the debugger. Um, and because this is backtracking, the like, the problem can be anywhere in the path. It's just like looking at the like one pass, like it seems that it's correctly backtracking. It doesn't seem to be anything obvious. So yeah. Hmm. Okay. In that case, let's just write some simple tests. So I want to verify that the pruning actually works as intended. That's one thing. I want to verify that these find empty and puzzle fields are indeed working as intended. Um, and for the matter, I actually want to one thing it definitely haven't tested well so far is the blocks. So block checker. Yeah, we definitely need to test the check and prune methods now. Okay, well, let's write a test for this first. Maybe something will pop out. Okay. So, there's a big block checker. So we want to test for the check and we want a test for the prune. And we want to, oops, not the cache. We want to add this as test. Block checker test. Oops. I will call it. Yeah. And reload, please. Okay, things are happening. Okay, nice. Default code. Why is it formatting in such a strange way? That's curious. Anyway, um, so I want to create a block checker. Right. So first I need a couple of elements. I don't really need like fancy, super big blocks tested properly. So let's just play with 3 elements for now. That will be fine. Sure. What were the vector of square type? Right. Um, oh, come on. Sudoku block type is a vector of pointers, right? Yes. So vector of pointers, which means I also need the actual. So this is the actual, this is the block. And yep, here I need to initialize it with not Sudoku block type, square. Didn't we have, where was it? Somewhere, oh yeah, square type, we called it. Where am I looking? Here, okay. So square type, so this will be our Sudoku setup, and then this is the block. So let's just create a couple of these with the maximum 3, because we will have 3 of them. And then this block will be simply a pointer to the first one, pointer to the second one, and pointer to the third one. And now we can actually initialize it with this. Yep. Actually, this I don't need this. So I could simply do this. Right. Okay, so now we have the setup. So now what we can do is actual 0, set it to 1. Actual 1, set it to 2. And actual 2, set it to 3. And at this point, we know that the check should pass because we have one of each number. So everything should be okay. So we expect true for block checker check. If we do then reset, then we still expect true, because if something is not set, everything should be still fine. But if we then go and say actual set it to, let's say, 3, now we should expect false. So let's see if this simple code works. I want the block check, okay. And it does, okay. So then let's have a look at the prune. So we kind of start from the same setup. Then we want to call, right, so if we call prune on 1 and 2, what we expect to happen is that basically everything will be set to 3. Okay, so the value on all of them should be 3 because we just pruned out everything else. Okay, that also passes. What else? Okay, if I do actual zero reset, uh, and then what I expect at this point is that I have two possibilities on the first element. Let's see. Yep. Okay, so this is all working, which is making me very sad because I still have no idea where the problem is. Annoying, annoying. Okay. So if the problem is not in the block checker, I can be setting up my blocks wrong, which is definitely a possibility. Okay. Let's write this setup checkers, right? Um, the strange part is that why is the formatting so weird? Okay, I will need to check my code style. This is very strange formatting. Oh, okay, because it tries to like line up these and then it screws up by adding the annotations. Okay, sure. That kind of makes sense. Um, hmm. Okay, this is quite puzzling indeed. I mean, am I just looking at the puzzle wrong? It is actually incorrectly pruned. Um, the problem is it doesn't look incorrect to me. Just like staring at it very roughly. Um, no, although I just noticed an error. So yes, we have definitely something wrong. So the error I noticed is this 5 here. Well, this 5 here says that there shouldn't be a 5 in this block, as in the 3 by 3. But behold, there are 5s in this block. So the pruning is actually wrong, which would mean I have my blocks set up in some broken way. Huh. Okay. That's And yeah, there's a one here. We should remove this one here. Okay. Yeah, okay. There's definitely something wrong with my pruning. Um, so we just edit this for the block checker. So I'm kind of trusting that to be actually correct. It should really mean that I'm setting up my blocks incorrectly somehow. So this was this crazy function. Okay. So oh crap. I already can see what I did. So I ensured that the checks are correctly reserved, but I'm not reserving these. But this should be okay. Shouldn't it? Because this I just pass here. Then I do this. No, this should be fine. Hmm. Okay. I will need to write test for this because this is very, very curious. Okay. So let's make another test. I'm getting the feeling that this will be the entire session today, just writing tests. But uh, that's what you should do. Right. Okay. Where is our test? Oh, sorted a little bit funky because of the name. Oh, that's fine. I guess I have to live with that. So let me quickly copy this again, so I don't have to deal with the includes and stuff. Oops. Right. So this would be the Sudoku test, and this will be the setup checkers. Right. And one thing we will need to do for sure is we will need to make this test a friend of our class because we actually want to check the internals. So there was a macro for that friend test, I think it's called. Yeah, okay, I don't like that. I will need to change. Yes, unfortunately, I need to do that. Um, here, I just want to do this bit of the crazy stuff. And the test we want to friend was called Sudoku test setup checkers. Right. Okay. So now in this test, we can actually touch the internals of this class, which is good. So actually, let's just reuse what we have. So let's just take this thing into our test. We need this. Right. So at this point, we should have the thing in memory. I actually don't need this part, honestly, but that's fine. So what I want to verify is that yeah, let's just pick some let's just pick some spots. So let's just pick the ones that are wrong. So if I do if I do block mapping for row 0 element 1 right, so let's just like first of all let's just verify very silly things. So there definitely should be 3 blocks at this point. And you should not be complaining because you are a friend of the class, so you really should. Let me just fix this because this is getting annoying. CEST, yes. Oh, wait a second. Somehow this didn't load it as a test. Uh, why is it running the main? Okay, that's weird. Somehow it thinks that Sudoku test is not a test. That's pretty strange. Yeah, I mean, but I'm a friend of the class. Okay, there's a slight issue that I just remembered. This cannot be in different namespaces. Yep, let's do that again. Yes, okay. I'm starting to hit the issues with my setup. I need to actually properly set this up as like libraries. Yep, that actually works. Still not being recognized as a test. That's so strange. Why do you not like it? Anyway. So yes, okay. So it indeed has 3 elements, which is good. So the very basic sanity check actually passed. Okay. But now what I want to verify is that the blocks actually make sense. So first one. Okay, let's just do this. Oh, let's just do this. Okay. I should just write some lambdas for this. Will not work. Because the lambda will have to be a friend of the class, which is asking too much. Right. The first one has to be the row, because that's how we set it up. So I can just do uh, 3.data size. Actually, data 0 size. So this thing, yes, so this is a block. But I also kind of need to access the. Yep, this is annoying. I need to put this into the block as well, because I kind of want to look at the elements of the block. Right. So this goes here. Input gtest gtest. Good. Yep. Okay. Yep. So now now I can access the element. So these 2 pointers should match. So the pointer of the test3 data 0 I. Let's just make it J so we're consistent across all our code, because that's how we index our columns. Should be the same as okay. Data underscore. Right. So this should be true. It's no. Which is very curious because. Oh, wait, no, this is an unordered set. Oh, crap, this can be any of them. Uh, this is annoying. Man, how do I check this? Yeah, so the problem is that the block mapping internally is an unordered set, which means that I don't have I don't have them in order. I mean, technically I can just make it a vector. Like there's nothing wrong with that. Anyway, just loop over it. So this way it just stays consistent. Uh, so actually, let's see. Did I break anything that way? Pink X white, it's fine. Okay, so there's yeah, let's just do this. Let's just do this everywhere. Okay. I think that should be enough. Let's see. Not another set. No. Vector. Block checker. Yep, every block is the same size. Same thing here. Oh no, actually I want an empty one because, yep. Okay, that should be fine. I think, no? What you don't like exactly about this? I'm it's nested multiple times. Right, now it's fine. Okay. So what the heck? Now we have 11 blocks in that space. Wow, what did I muck up? I mean, these are just pointers to the block checks. the way that I initialize this. The heck? Wow, today is just not my day, I think. I think I screwed up completely somehow. This would mean that we're pushing back into the same thing many, many times. And it's a weird number, 11. Like, that's a very peculiar number. How could we end up with 11? So again, like we have a two-dimensional array of block of arrays block checkers, right? So that's correct. The same here. And these are empty vectors. Then we only ever call setup checkers in the constructor where go and just push back. Let's just see for sanity checking. Okay, so this actually looks the same. So it could just be that our test is being weird. But I mean, why? How could I end up with 11? Wait, am I copying the data somehow? Wait a second, but this should not be happening, I think. But let's just make sure. Let's just make sure we get rid of any chance of copying, because this class is definitely not set up to be copied around. Let's see. No, that definitely wasn't it. Yep. This really means that I call. Yeah, okay, there's something really broken in my block checker. Not my block checker, my setup of my blocks. I'm mucking up the indexes somewhere completely. So let's just start sanity checking this thing. Okay. So if I just do rows, only rows, then I run the test, which is 1. So this is perfectly correct. I have one thing because it's in one row. Okay. Then let's add columns. I'm kind of expecting this to be this just return 2. Yep, so columns are fine. So I have screwed up something in my block setup. Okay. So let me actually quickly jump into the debugger. Uh, so B size is 3, that's correct. So now I go 1 to 3, 1 to 3. So this iterates over the blocks. So this is inside of one block. So it's kind of the same as like this piece of code. So within this piece of, oh, I already see the problem. Oh, okay. Yep, this is not our index. Definitely not. It should be XY. Pushback checks. Yep. So actually, let's just see if this fixes the entire problem. It probably will. And yeah, now yeah, okay. Wow. Okay, that was very silly. Uh, I knew it would be something very stupid. So actually, let's just see. So let's just comment out the excessive code. What I'm interested in. Okay, just a second. Da-da-da-da-da. Okay, a little bit of timing information. So I want to basically have this block load Sudoku. Then try to solve it. There's definitely like a diff time or something like that, I'm sure. Maybe not, I don't know. It never really worked. Oh, there's the system clock, chrono. How do you use this thing? Uh, returns. Okay, cool. This is what I'm looking for basically. So instead of this, I want this. Okay. And then basically this thing again, but now we want to have this block just before we solve it. And yes, we want to include the pruning because I mean that's part of the solving. Okay. Let's just get rid of all the other crap. Okay. So let's adjust optimization level. This. And I'm sure there's a better way to do this. I will need to look it up at some point and improve my CMake because I don't really use CMake that much. Right. Let's see. Um, that's a big difference. I forgot to change this. Okay, so let's try a couple more times. Yep, it seems pretty consistent. So just doing a very simple pre-pruning, we basically go from 4 seconds to 0.8 seconds, let's say. We are still just guessing, like there's nothing nice we are doing. And just for the heck of it, I want to see if now with this improvement, I can actually solve the 16 by 16 Sudoku. Because that would be actually neat if basically this very simple approach is good enough for 16 by 16. That would make me very happy. Right. And now we just want to change this to let's get the Sudoku. Let's change the names here for something better. Refactory name. So this will be. Come on. Okay. Enter. And this will be Sudoku 16 by 16. Yeah, okay, I only want to refactor this. I didn't rename it. Okay. Right. Now this needs to be 16. Okay. Let's see. Let's see if we can solve 16 by 16. That would be very nice, but this will probably take a while. Which is great because I anyway need to take a short pause. So I will be back in like 5 minutes and we will see if this actually got solved or not. See you later. Yeah, okay, I'm back. So no, unfortunately 16 by 16 is still impossible for the solver. Um, but I'm actually curious. Like I know that backtracking is kind of unusable on 16 by 16. That's not really a surprise for me. But I wonder, um, if we go back to the perf, um, so this is the running slightly older version of my code, but like perf was reporting that we are spending a lot of time um, in the check routine. And having that kind of profile is actually good because, well, it kind of tells you what you should optimize. Like if I'm spending 85.5% in one specific function, well, if I make it twice as fast, I'm making 85% of the program twice as fast, which is great. So let's try something. I mean, this is supposed to be just me having fun with a bit of code and Sudoku. So let's just play around a little bit. So let's go to the block checker. One thing that's kind of possibly slowing us down is this vector. And I mean, actually, if I go to the perfect port, there should be a way to have a look at the code. Um, yeah, unfortunately, I'm not great at reading assembler. But this actually does look pretty dense, all things considering. Uh, and honestly, it does look pretty inline to me. Like there isn't anything crazy happening here. Um, and we seem to be spending 12% just doing end, which kind of makes sense. Hmm. So can I make this somehow better? I wonder. Let's see. Let's just add some little helpers here into the square thing. Uh, so let's just remember our picking type. Because then in the block checker, in the check routine, what I could do is instead of that use a bit set. Um, you don't know char bits. Why do you not know char bits? Where is this thing defined? Oh, it's not char bits, it's char bit. Okay. Mm, what the heck? This should. Mm, oh. C limits. I wonder why sometimes it just sees the inputs just fine, sometimes it straight up is confused. Xelan can be weird. And what's the constructor of bit set, I wonder? Okay. So std bit set, constructors. Mhm. Oh, yeah, we actually want the default one, yes. Uh, so then what we want to do is if isn't, what are you complaining at? This should be fine. Uh, what? Ah, never mind. Okay. Okay, let's just see if this has better performance. Probably not. Yeah, no, this is actually worse. Good. Um, it's always a joy when optimizing things and ending up with a worse result. Um, I mean, there is actually a way to write this in a different way. So, so this check can be also expressed in a different way. If you think about it, if we just go over the elements and ignore like, oh, have we seen this before or whatnot, and just set the bit to true if we see a value, then at the end of the loop, uh, yes, then at the end of the loop, uh, we can basically check if stuff is correct. So what we kind of expect is if we have we remember the number of unset elements. instead of continuing, right? Uh, okay. Right, I still need to continue here because otherwise this other line just screws up things. Hmm. Okay, we actually don't need this line. Uh, yeah, I do need to do continue here. That's unfortunate, but that has to happen. And then we just set this, and then I do. Oh yeah, I do need that set. Yeah. Screw it. Let's just do it the hard way. So instead of that, I will actually have a pivot element. So I don't have to continue. Okay. So now this loop should be way more optimal because I'm not really jumping around. But at the end, what I need to check is if present.count equals on.size minus unset, but there is still the pivot element. So if I have if unset is not 0, then I will basically the count will return one more than it should. Um, okay, so it should be this horrifying thing. So okay, this needs a little bit of comments. So this number of unset elements, we return value equals 0. So this will all map into the 0 bit of this thing. They will set it. So yeah. I think this should be correct. Let me just quickly check. Um, da, 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 da. Right. Let's just see how fast this runs. Oof. And we broke it. Okay. So this is not working somehow. We remember the number of unset elements. Present set. This is correct. So okay, this thing should be true if we don't run across, like if we have a filled block and we don't run across any unset elements, then this is true and no collisions. So the number of set bits is actually count returning that. Let me quickly check. Bit set count returns the number of bits set to true. Yes, okay. And set sets bits to true. Yep. Um, uh, should be on this side. Right. Okay. Because so the count will return one more than it should if we have any unset things, but then the total number of unset things should be discounted from the element size because that's we have that many. Yep. Okay. Let's see. Yeah, that's pretty much the same as the vector bool. Yeah, I don't think these are helping because I think the actual problem here is these are way too small. I mean, this for a 9 by 9, like this loop is just tiny. And in particular, this thing is actually jumping around the memory like crazy. Because this is run on a block, and a block just has pointers to specific elements in the Sudoku puzzle. So I think the actual performance problem here is not anything related to the code at all. The actual problem here is that unfortunately this is super hostile to CPU caches. Yeah, I think that's the problem. Um, yeah, so I might just revert this entire thing back to the old vector bool. Yep, that's slightly faster. It's funny actually. Okay. So this basically means that I actually need to bring the heavy guns. The good thing is that we do have a nice starting setup that actually works. Yep, so kind of did that. Right tests, we kind of did at least a little bit of that. Did that at some point. Right, okay. So we kind of have the version 3. Um, we have the basic pruning. Well, actually, we have pruning altogether. We can just prune out a value out of the block, which is kind of all we need. So let's talk a bit about the next steps. And now we definitely know that 16 by 16 we cannot solve. So the next step I want to do is actually to implement some of the very basic pruning algorithms. So for solving Sudoku, actually let me grab an example. Right. Okay. So there are a couple of very basic algorithms. So one of them is just the pruning. Then like for human consumptions, these are kind of called differently, but honestly, from a machine perspective, these are all the same. So, okay, let's see. Can we... So if I look at the ones, the one cannot be here, it cannot be here, and it cannot be here. So if I would basically prune out these numbers, what would happen is that the only place where I can have a 1 is actually in this space. So, and technically I can, like after the pruning is done, like I can still have like other numbers there. But the important thing is not 1 will not be present in any of these other spaces. So this is kind of like saying that the number of occurrences in a block equals 1, then obviously that space needs to be that number. Let me just write this here. And funnily enough, because we actually don't care about jumping immediately to the solution, you can kind of extend this idea. So if we have, because from the solver perspective, what this means is I can prune out all other numbers from this space, right? That's kind of the important part of this rule. The fact that we are actually solving a number is not that important. The important thing, I can just remove more like possibilities from a space. That will definitely never be true. And because of that, when I'm doing my backtracking, through the puzzle, I can just skip over those because like they don't exist anymore. They're not possibilities anymore. So let me just write it down. So from the perspective of the solver, we can prune all other numbers from that space. And you can have an inverse of that, which is if a number of possibilities for a block is 1, that means that basically that space, like in our code, it would return is set, and the value would return the specific value. So we know that that space is that number, and from the perspective of the solver, we can prune that number from all spaces in the block. So these are the two kind of basic ideas that keep repeating. So the first one is if something can only go in one space, then obviously that space has to be that thing. There's no other possibility. If a space only has one possibility, that obviously, again, that space has to be that number and nothing else can have that number. But you can extend these to basically any number of numbers. So let's just go back to this. So okay, so here this was easy. We just set it to 1 and we are super happy. I don't know if I will be able to demonstrate it on this puzzle, but okay, let's say, and this will probably be complete nonsense, but basically, let's say we have figured out somehow that these two spaces, the only options for these two spaces is 3 and 4. Well, since we have two spaces that only can have two numbers in between them, that's kind of the same rule. It means that 3 and 4 cannot be anywhere else in this block. And in this case, this actually applies to two blocks because it applies to, this block, but it also applies to this block. And again, there's an inverse of this number, of this rule. So if, okay, let's just do something. 3, 6, 7, 8. Okay. So again, if this was a situation where I have, 3, 4, I can just remove the 3, 4 from these spaces. But inversely, if I have this kind of situation, well, now I have two blocks. And for the numbers 3 and 4, these are the only two blocks where the 3 and 4 can be. So by necessity, they have to be here. So I can remove the 5, 6, 7, 8, 9 from this block, like these two spaces. And that's the inverse rule. So using kind of this pruning technique, we can just like ratchet up the number. Of course, like if we set the number to size of the puzzle, like it is completely pointless. And since these rules are kind of symmetric, like if we basically have like five possibilities, well, since the rules are symmetric, like there has to be a 4 possibility situation in the other 4 blocks. So there are some weird situations where like you see one of them and not the other, but generally it should be completely symmetric. Like you should be able to basically conclude that yes, like obviously, like if I see a 5 set, then obviously the other spaces have to form a 4 set because there's no other way. Like that's just how Sudoku works. So kind of next time we will look at implementing these kind of pruning rules. And this is slightly starting to touch on like the human complexity, because for easy puzzles, you maybe sometimes go to doubles, but easy puzzles basically should be solvable by doing the singles and maybe, a couple of times look at the double. And the higher you go in this one pruning technique, the harder the puzzle is. If you kind of need to look at 4s and 5s, that's an extremely hard puzzle. And of course, there are like slightly more involved, basically overlapping blocks techniques that we might implement later. But this is kind of the idea. Like we take the human approach to pruning the puzzles and we kind of slightly tweak it by making it more general. So again, like we will just have one pruning method that just takes like the what is the like number I should be looking at? Like, oh, I'm looking for singles, doubles, triples, quadruples. It will be one function that will do that, but we will just, in a very simple way, just loop over that. And if we just want to generate simple puzzles, we will only allow it to go to like doubles, for example. And if we want to generate like more interesting puzzles, hard ones, then we allow it to go up to like quadruples, for example. But the logic of the pruning will be always the same. And the great thing about this kind of approach is if when you are solving the puzzle, doing this pruning is guaranteed to be basically something that you never backtrack, because this is, I mean, these rules are just like always true. Like if I see a 3 and a 4, and those are the two only options, then obviously I can remove 3 and a 4 from like all the other spaces in the affected blocks, because that's just an like how Sudoku works. So there will never be a case where we would like undo this kind of operation. So for solving Sudokus, this is actually very backtracking friendly, because we can just do this kind of pruning and not really care about, like, we don't have to store any kind of state, because if we just did the pruning, then there's no reason to undo it ever. So yes, I mean, that's kind of the idea for the next time. And hopefully implementing some of this logic, and I think even just going to doubles, will allow us to solve 16 by 16 puzzles very easily. And it should also allow us to jump the speed on our solver drastically. So you have seen that when we run this, we went from 4 seconds to 0.8 seconds essentially. This should improve drastically if we introduce this kind of pruning algorithms. Like we should be very much able to solve thousands of Sudokus per second easily. Because these algorithms really cut the search space drastically. And for like human purpose, you should be actually able to just solve Sudokus just using these pruning rules. Like you basically never do backtracking, because that would basically equate to guessing. And a good Sudoku puzzle doesn't have any guessing. You just prune the space until you end up with all the spaces having only one possibility, and that's how you solve Sudoku. So yes, we have a lot of interesting stuff in front of us, and I think I will end for today because again I have been streaming for quite a while, and I should just go and relax, so I'm ready for work on Monday. uh, have a nice day, everybody. If you are watching online, then thanks for joining. If you are watching the recording, then uh, good luck with watching the recording and maybe just skip over the boring parts. Uh, I will actually try to do some sort of Redux versions of these live streams at some point, but that will take a lot of time in editing, so I'm not sure when I will be actually able to get to that. Anyway, have a nice day, nice evening, nice morning, whichever applies, and see you next time.